Hello, good afternoon, everyone. Welcome to the fifth talk of the Monsoon Cafe 2022. Myself, Thanangka Chutia. I am a second year PhD student and I am working under Professor Arindam Chakrabarti and Professor G.S. Bhatt. So, before going to present one of the papers on the diurnal cycle of the propagation of the Western Ghats, let me tell you in brief what is the diurnal cycle in different regions of the so, what is a diurnal cycle? If you see any pattern that repeats itself in every 24 hours, that is a diurnal cycle. For example, like the temperature diurnal cycle or the rainfall diurnal cycle in the meteorological department. And there are other diurnal cycles also, like the diurnal cycle of the photosynthesis in the biological sciences. And anything in any field which repeats in 24 hours, we can consider this as a diurnal cycle. Now, generally, we discuss most about the rainfall diurnal cycle, and this is how the rainfall diurnal cycle looks. Over the length, mostly the diurnal cycle peaks during the afternoon hours, and in the oceans, it mostly peaks in the late night or in the early morning hours. But this is not so for all the regions. For example, in some regions, like the mountain basins, there is late night and early morning maxima also can occur. And also in some partially enclosed seas like the South China Sea, the afternoon maximum of precipitation may also occur. Now, in order to say why the diurnal cycle is important, now I have plotted the frequency spectrum of the time series of the rainfall for the month of June from the year 2001 to 2020, and it is average about the whole overall India. It is the ERA 5 reanalysis data set, the hourly data set, and you can see that the peak occurs for the diurnal mode. The amplitude peak occurs for the diurnal mode, and this is the semi-diurnal mode, and the rest all oscillations peak is much less than the diurnal mode. So if you are dealing with a data set which has an hourly variation or half hourly variation, we can't ignore the diurnal cycle.
This is where?
This is from ERA 5 reanalysis. ERA 5 reanalysis. This is average over all India. I have average over whole India.
Whole India.
Whole India.
So why do you take this semi-diurnal scale then?
Because there's hourly data set, so this semi-diurnal peak is also coming in this way.
Yeah, but almost same as that. I'm surprised. The diurnal peak and semi-diurnal are almost same amplitude, which is surprising.
Yeah.
Is it that because you have averaged over
average over all land region maybe because of that?
If you take a smaller domain or then you will get positive. There are two different times.
Yeah.
Right,
the Himalayas and some of those regions have two peaks. At the one continental 5:30 p.m. but the other one at this early morning. So because
yes,
all of India,
almost all regions, if you average it, you will get almost two binaural peaks will be there. You can see here in this paper it is discussed. I've just noted the hourly because yes. So another is that if we understand what is the driving force mechanism responsible for the diurnal cycle of a particular region, we can understand the mechanism that is responsible for the local weather and the climate. And also, if studies have also been found that if we can improve the errors in the diurnal cycle prediction, we can improve the prediction of the larger time scales also, because almost all the models can't predict the diurnal cycle accurately. So if there can be improvement can be done in the diurnal cycle, we can make improvement in the prediction of larger time scales also. Another thing is that the understanding of the diurnal cycle will help us in understanding the surface energetics as well as the radiation pattern. And there are many more examples because of which the studying of the diurnal cycle becomes very important. And also for various regions like the of some complex topography like the Western Ghats is also important. So here I'm presenting a paper which deals with physical processes that controls the diurnal cycle of the convective storms in the Western Ghats. It was by Krishna et al. And it was published in the Scientific Reports 2021. So here, this was the study region. So this red box, this is the one they have described as the coastal region. This yellow box, this is the upslope regions, and this the blue box is the mountainous or you could say the Western Ghats region. And this magenta circle, this is the ground-based X-based radar measurement location, the data set which they will be using for the ground-based radar data. And this is the data set they have used. And directly from that radar location, for the windward side and for the leeward side, for both the radar data set and as well as the trim data set, they plotted the normalized distribution of the frequency of the diurnal cycle, and they found that a bimodal peak is found for both the trim as well as the radar data set for both the windward as well as the leeward side. And but there is a gap of 1 hour for almost 1 hour for the radar and the trim data set for both the windward and the leeward side. This is mainly because the temporal resolution of both these are different, and also the propagation part as well as the resolution, volume size, the sensitivities, all things are different between these two sides. So there is almost a 1 hour gap, but the peak has been shown by both these two data sets on both the two regions. Another thing is that the intensity of the magnitude that is more in this leeward side than in the windward side of the two locations.
So this also has a
Yeah, this also has got peak.
double
Peak is there. Now, this is the special plot. Like they have differentiated 3 different regions, based on the mean sea level. One is when it is less than 50 meters. So they have considered this as the coastal and oceanic regions. The between 50 to 500 mean sea level height, they have considered this as the upslope regions, and greater than 500, they have considered this as the mountainous regions. So what is found is that in a bimodal peak is found in this coastal and the oceanic regions, and in this which is not much prominent in this upslope and then in the mountainous regions. Another thing is that the morning maximum occurs in this coastal and the oceanic regions, but in the upslope and in the mountainous regions, the maximum occurs in the afternoon hours. And also the third thing is that the magnitude is more, it's the highest in the mountainous regions, and it's the lowest in the oceanic regions, and it is intermediate between the oceanic and the mountainous regions in this upslope regions.
So when you say oceanic region, what extent are we talking about?
Extent means
When you say oceanic regions, it's all of the cards we're talking about there.
they have this box. They have this.
This is the expand radar data, right?
Yeah.
That won't go more than about 100 meters, 100 kilometers into the sea.
So resolution stats is in this data set. They have defined it. So up to what resolution they have used.
Yes, so that's about 100 kilometers only, because it is less than 74, right? And that is 73 is about that kilometer, about that degree.
Yeah.
So the expand has a very short range.
Yeah. And 2 more parameters they have checked in order to see the intensity of the convective storms. So one is the precipitation flux, and the other is the vertically integrated liquid over the radar domain. And they have found that in the afternoon, the intensity is more than in the morning hours, which shows that the intensity of the convective storms is more in the afternoon region, in the afternoon hours, than that in the morning hours. So based on the now they are trying to explain the mechanisms using the ERA 5 surface winds and the surface temperature, and this is for you can see that as the day progresses, the temperature of the land increases, but the ocean's temperature doesn't vary much as the day progresses. And another thing is that the wind vectors, the magnitude of the wind vectors are more in the oceanic regions than that over the land regions. But as the day progresses, the strength of these westerlies increases over the land region. So in order to differentiate how the westerlies, how the wind patterns behave differently in the land, in over this radar domain during the night and the day. This is during the night. In order to calculate during the night, they have calculated the wind speed differences and the wind vector differences between the time 230 LT and the 2030 LT, and this color controls is the difference of the wind speed, and this vector plot shows the difference in the wind vectors. You can see that during the night, the direction of the wind velocity is from the east to the west, which shows that from the upslope regions, there is a propagation of the wind velocities, propagation of the wind from the upslope to the coastal regions. And this, they have said this reason is because that during this time, the land surface temperature is less than that of the oceanic region, and due to this contrast of the temperature between the land and the ocean, there is a movement of the winds from the upslope region to the downslope region. And again, there is a continuous movement of the southwesterlies going on. So this will result in a convergence, low level convergence over the oceanic regions, which results in the convection in the morning hours. This can also be shown by the VIL plots. The number of VILs are more over these coastal regions than they over the mountainous regions during these morning hours. And also for this 18° north latitude, they have plotted the vertical cross section of the mean speed, mean horizontal wind speed, as well as the difference, as well as the deviation of the mean vertical velocity, deviation of the vertical velocity from the mean with this solid contour plots. And this is in the pressure coordinates. So this solid curve indicates updraft, and the dotted curve indicates the downdraft. You can see that during this morning hours, this red mark indicates that this is the coastal region. During this morning hours, there is updraft of velocity. This can also be shown by the deviation of the divergence from the mean, surface level divergence from the mean, and you can see that there's low level convergence over this coastal region during the morning hours. So they've told that in the development of the land breeze downslope winds in response to the land sea temperature contrast is responsible for the nocturnal maxima over the oceans and the coastal regions. The same things were done for during the day, and over the day you can see that the direction of the wind were from the east to the west, and same they are plotted from this VIL plot. So the number of VILs are more during this afternoon or the evening hours, and you can see that now these updraft velocities have been moved to the mountainous regions during the time 14:30, where the peak of the rainfall mostly occurs. And this can also be proved by this one low level convergence, low level divergence, and you can see that negative this convergence is over the mountainous regions, which shows that the orographic response to the prevailing monsoon flow from the surrounding oceans that is superimposed with the land sea thermal contrast, it is responsible for the afternoon maximum of the occurrence of the convective storms on the higher altitude. One more thing they have found was that in the afternoon, the intensity of the convective storms was greater than that in the morning. So there are many theories that is responsible for conversion of shallow to deep convective storms, but the most they want to describe here one is the moistening of the mid-troposphere. So now for looking the moistening of the mid-troposphere, during which time of the day it occurs, first of all they have made the specific humidity difference between the day and the night. So wherever you see positive, that means specific humidity difference is more during the day, and wherever you are seeing as negative, that means specific humidity is night. So you can see that during the ocean, over the ocean and the coastal regions, the specific humidity up to almost 800 hectopascal or 750 hectopascal, you can see that. Sorry, up to almost 950 hectopascal, you can see that it is the specific humidity is more than night region. During the night time, and during the daytime, the specific humidity is more about a mountainous region. This is the vertical velocity profile, that is the omega dPdt. So you can see that the intensity or the strength of the vertical velocity is more in the afternoon hours than that in the morning hours. One more parameter that is used to check the instability is the equivalent potential difference. As we know that for an unstable environment, the equivalent potential temperature will decrease as we go from bottom to top. So this is the difference of the equivalent potential temperature between 500 and 850 hectopascal. And you can see that all the values are negative. This means that these two environments are unstable. But the thing to notice is that the gradient of these between any two locations is much more over these mountainous regions during the time these afternoon hours than that during the morning hours, which shows that in the afternoon hours the instability is more over these mountainous regions, and hence this instability is resulting in the moistening of the mid-troposphere, and this mid-troposphere moistening is responsible for the deep convective storms over this particular region during the afternoon hours. So in a summary, you can say that the convective storms show a clear diurnal cycle over different topographic regions, and a prominent bimodal distribution is found over the ocean and the coastal region, which is not much prominent over the mountain peak, but the frequency is different. The afternoon peak is stronger in the afternoon peak is stronger over the high altitude region, and the morning peak is stronger in the oceanic regions. And the afternoon maximum is related to the local topographic lifting, and which is also aided by the solar heating. And the morning peak, it is responsible for the low level convergence of the winds that is coming from the mountain to the coastal regions, as well as the monsoonal flow, which is prevailing over that region. And during the afternoon hours, the convective storms are deeper than that developed during the morning hours. This was mainly because of the lifting of the air, as well as the underlying thermodynamics like the metropospheric moisture is responsible for this deeper convective storms. So then we'll see what is going on for this monsoon 2022. Right now, there is a deficit of -10% of our whole India region. And this one we can see that except the east and the northeastern region, rest all are having a negative deficit of rainfall. And this is also seen that in this northeast and in this little bit of south, others all are having a deficit of this one. And this is the forecast based on initial condition of June 8. So you can see that for the next week, this is the pattern, and the northeast might be having the lesser amount of rainfall, but this is based on the initial condition on yesterday, that is 29/6/2022, and by the end of this week, northeast might be having less amount of rainfall, which may be reducing the flood situation which is going on right now. So thank you, Krishna.
Thank you.
You talk about the paper.
Ah.
So it's based on some particular season or it's just a random day?
It is on a season, on season, I think 2008 JJS season. The data observations was, but all other observations in order to calculate the climatology, they have taken 11 years season of JJS.
So why did the coastal region have the second peak at all?
Pardon, sir?
The coastal plot you have was bimodal, right?
Yes.
So the first peak you explained based on the dynamics right now, right? So why is the second peak there?
Second peak is not explained in this paper, right? The quiet afternoon peak is.
You say the cold air from the top mountain comes down the mountain.
That is.
At the top of the mountain, air gets colder, and that comes down and meets the warm air and records. That's what he said.
That was for the morning peak.
Huh?
That was for the big peak that he had. But there was a second peak there. Right?
The second peak is the night peak, right? That's what. First peak is
the morning.
Second peak is the night. Huh?
In the coastal region, is checking.
The morning peak.
Morning peak.
First peak is it cools at night, the air, and the air comes down the slope. That's the name. What the name for it? The name for that. So that's you can keep when you are in the mountain. Cold air comes down the mountain, and early morning it meets this air from the ocean, which is warmer. Yeah.
Okay, I came late, but there's a paper by Sandeep Sahani from our center itself who looked at dream data, Diana cycles over different parts of India. So maybe I don't know whether it's familiar with it, but it could also be developing Diana cycles. Yes.
Okay, no, thank you. Yeah, we are going to complete 1 month of the monsoon, so it's good to have a big. Huh? This side or this side?
To share the screen.
Okay. Okay, thank you. Yeah, so Thanangka already shown this, but I just want to add one more day. Just got the data the last half an hour. So The key point about what's happened so far is that we are about 8 days of above normal rainfall in June. The rest of the time below normal. And if you look at the forecast based on 9 June, they were quite right about the low rainfall here and the rainfall increasing here. Very good, but they failed that. So the last week's, this week rather, they said plus 24 and it's more like minus 24. Okay, the series there. Now all of you have followed this discussion know that generally the forecast in the third week is not good. We know that, but it is a wrong sign that worries me. So that's a part, and you can see here that we have reached 142 millimeters in June. One more day is tomorrow, maybe 600 millimeters. So 150 we reached, which is not too bad. It's 20 millimeters below normal. So it's not above normal as Aditya was hoping. It's below normal. Yes?
Which forecast?
Huh?
Which one forecast? IMD forecast or NCMW?
Which one?
The forecast.
Forecast IMD. Yeah. Everything is IMD. I'm not, everything else is NCMW I don't see. Only IMD gives me these numbers. See, these numbers, I get IMD is all India value. Okay? So they give a 4-week forecast, underneath there's a all India value.
But we have so many models.
Huh? No, this, I think this is multi-model green, I think. Yeah, this is multi-model green. Yeah, so look at the, again, from the IMD, although they got the numbers wrong, I like to put the trend is right. They correctly predicted the declining rainfall from 19th to 23rd and increasing, then they failed here. But now they are showing an increase. So I would say that actual rainfall, they are not getting it right, but most of the time, the weakening of the monsoon and strengthening, they are getting it roughly right. So that's worth asking how they're getting that right. And the last 2 days here, they are showing an increase. This may not happen. This is a very high rainfall prediction. But they're saying it's going to pick up in the next few days and then slightly decline more. So we'll see that next week. Now, first thing is, you remember the first lecture, SkyMet forecast 107%. So they are wrong. Okay, we are 20 millimeters below normal. So that would be, it will be 20 by 170. So at least 10% below normal. And they are saying some of the, so they are wrong about this. Okay, and IMD didn't make any forecast for June. They were not given enough forecast. Now, June, of course, doesn't tell you anything about the whole season. So this year we are somewhere here, close to 150, and I've given one number for 2015, and it was 189.5. The reason why I'm giving this is 2015 got out a very good start. Okay, and SkyMet had predicted above monsoon rain, above normal rainfall in 2015. It was an El Nino year. IMD took the courage and made a forecast of below normal, but the first month was very good. And so was the next month. So very soon IMD got into a bit of a trouble in the media saying that IMD's forecast is wrong, but later on it turned out this was a drought year. So June tells you nothing. That's why I'm always puzzled by the fact that the media and everybody else make so much possible onset date. Onset date is great, of course, rainfall in June is below normal. But that doesn't tell anything about the rest of the season. Okay? So the rest of the season depends upon July. So July is the heart of monsoon in India, and if July goes below normal, we are finished. Okay, so the next 1 month is going to be very, very critical. And we have discussed that earlier. Earlier, this jet was tending to go like this, much more. Now, slowly, with the RTCC being somewhere here now, the jet has gone into its normal position and bringing the moisture into India at this point. Okay. Took a long time. I don't know why. Compared to the climatology, this is a little late. And now let's look at the MGO, which is telling us how situated it is. So today's MGO shows clearly that upper level over India is diverging, and that is favorable for, of course, monsoon being good, but it is moving out of India in the next 1 week. So things will not be that favorable, and by the time we go to 7 to 30 July. Okay, it is neutral. It is not either convergent divergent. But after this, if this convergent flow at the upper level comes to India, we are in trouble. Now, this is quite critical. I'll give an example of what happened in 2002. So 2002 was a very unusual year, 20 years ago, and there was a major failure of monsoon in July. Okay, I think the biggest in the last 150 years. The July rainfall was 50% below normal, which has never happened. Okay, and it happened very suddenly. I still remember it because there's a lot of discussion in the center on this issue. And what happened there? So this is the divergent velocity potential anomaly at 0.25 sigma at the upper level, whole of June. Okay, whole of June was not that favorable, but June rainfall was above normal in 2002. Everybody was happy. Then look at July. This is monthly mean. I'm showing first. Okay. See, July, the whole thing turned over. There was a huge upper level divergence here, which is associated with this upper level convergence here. So this was there for almost 15 days in the first week of 15th July. And there was no monsoon over India. Okay. Very rare event. As a matter of fact, it has not still been fully understood. People are still debating why it happened. Okay, you can always blame the El Nino, that's a villain there out there, but that alone cannot explain such a long break and at the peak of the monsoon season. Now let's look at it a little more closely. Now this is the all India monsoon rainfall from Kripalani's analysis. Normally all India rainfall, and he has drawn two curves, the 60-day mode related to MGO and the 15-day mode. You see clearly the 60-day mode which went against us. Okay, right during the period, there was a big period where rainfall revived due to the 15-day mode for a short time. And so this was one which really dealt a big blow. And then in August, things got a little better. Conditions were a little more favorable. So August was actually normal, and September was also normal. But we couldn't make up for that. That failure was so large. Instead of a rainfall of 290 millimeters in August, we got 136. I'll put the number down very soon. Now, what's interesting is if you look at the satellite data, in June there's a beautiful northward migration of the rainfall band from the equator all the way to Gujarat. Okay, it rained heavily in Gujarat in the last week of June. Everybody was happy. Okay, and then suddenly the next 15 days there was nothing. Okay? And next was a week northward migration. Then the real one came in August. So this one makes it complicated. There was a nice event occurred in June, and monsoon was there all over India, and June was above normal, and then all of a sudden it switched off, and there was nothing. Okay. Now how sharp that was, I'll show you how sudden it was. Okay. Now this is now I'm showing you 10-day average. Okay, not 1 month. So this is the last 10 days of June. Okay, you can see that India is slightly getting into upper level convergence situation, but not yet. But look at 10 days later. India is right in the middle of upper level convergence. That means descent over India. Okay, and so this is what remains stationary. That's a key point. Remember that the MJO, which propagates in the equator, doesn't travel at constant speed. If it did, life would be very easy. But it had a lot of variable speeds. Okay. And so that year, for reasons even today is not understood, it was somewhat slow in traveling. So it was over this region for 15 days of July. Okay. Now, to show the more dramatically, I have plotted the omega at 500 millibar, okay, anomaly as a function of time going down, okay, from 22nd June to 22nd July, okay, and look at the region between 70 to 90. See how strong the descent is all the way from 25th June all the way to 18th July. Okay. So this was the most unusual event I have seen so far, and so this should not happen. So in the coming month, we will watch for it. It probably will not happen because remember, this year we still have a La Nina, although it's weakened somewhat, but it is not an El Nino. So anything, so the point is that, let me explain what is the trigger. See, when there is an El Nino in the Pacific, there is a lot of convection here, right? And this part, this is July. And so this convection will have a large upper level divergence, which will have to converge somewhere. If you are unlucky, you converge over India. You can converge over Africa, you can do other things also. But in certain situation, if you are unlucky, it converges right over India. Okay, so that is the thing we have to worry about. That may not happen this year because of La Nina. Now let me give the numbers. So I put all the numbers down earlier, the first lecture. Now I added the 2002. Okay. Normal rainfall in June. Look at July. I must check. I don't think there has been ever any year in the history of monsoon data where the July rainfall is lower than June. I've not heard of it. If anybody see that, let me know. This is unbelievable that July has less than June. August recovered. It made up for the things, but it didn't recover enough. This is sort of normal rainfall. September, slightly below normal. When he added, he got one of the lowest rainfall in the last 50 years. Okay? Lower than 2050. So about 170 millimeters below normal. Remember that. So what I want to point out is that all that was caused by just 1 month, the month of July. So July is the heart of monsoon. We just cannot afford a break in that period. Now, I'm just comparing here forecasts made by ensemble forecast of GFS, ensemble forecast of the Taiwan model. It's also GFS really. And then you have ECMWF. So I would say that all of them got the South India got roughly right. They didn't get the Northeast monsoon right. No, sorry, they got Northern, but I'm sorry. The color is not right. This is a high rainfall. Okay, this is this, and this is so they're not anomaly here. So I can't really this is normal rainfall here. I wish there's an anomaly easier. So I would say they got roughly the south and this right. And only thing is that according to IMD, the drought prevailed over a longer region South India than what these models show. Now I'm comparing both from IMD. This is the forecast from IMD based on 9 June. This is the observation from 9 June, 15 June. Slightly 1 day displacement than usual. And so if we compare the two, same color bars and so on, I would say not too great. Because look at Gujarat. They got totally wrong. Okay. So they had forecast high rainfall over Gujarat. That did not happen. And then Northeast is okay. Because the Northeast is right. South, except, no, yeah, all of them got it wrong in South. Sorry, the reds are similar. And this one thing is what is observed is not seen there.
What is yellow color right?
Yellow color is very low rainfall. Yellow is what no? They use a name which means almost no rainfall. Although it's not true. Yeah, above 50% lower. That is, yes, if you look at, when you read the number, you can see in Orissa it rained 13.6 millimeters instead of 40, so it's minus 71%. So above 50% lower is yellow. Okay. This is below but 47%. So that is the distinct damage. Okay. Yeah, this already Thanangka showed. And what I want you to notice here is, if you believe the forecast 4 weeks ahead, is the development of negative rainfall anomaly here. Okay? Although the RTC that seems to be there is July 14th. After that, there is sign that this is weakening, and this or we have all your positive anomaly, negative anomaly rainfall. So that is what we have to look for whether it will happen or not. And this is NCMWF I would say quite similar. And here they are saying almost normal. Now, what is the El Nino now? El Nino now is minus 0.3, 3.4. So it is rapidly rising. Okay. Now, this could be a temporary phenomena. Things do go up and down in that region. But it was for a long time minus 0.75 from about last October to this. It's not much, but now it's rising. We hope it won't go into neutral. But let's also understand why this sharp rise is occurring. It's due to some phenomena which I mentioned, but I'll now show you some results. And this just to remind you how the 3.4 has impact on the Indian monsoon. And what I want you to follow this year. I hope we can remove this. Can this go? This thing is the stop sharing thing can be removed. But can you just get rid of this? Hide. Yeah, right. So the point I wanted to focus is our 3.4 is somewhere here now. It is going up here. So this is very critical because 3.4 was around -1. Of course, JJ is average, not 1 month. Then chances are we have normal and above normal. As it goes towards neutral, we see the range of variation. So it's very sensitive as you approach. So we should hope that it doesn't go close to neutral. And a lot of discussion has been there now in Nature News last week, so-called triple La Nina. That is 3 consecutive Decembers in which temperature is close to beyond -0.5. This is not common. So there have been examples of previous years when year 0, year 1, year 2, year 3, and so on are all below the threshold of -0.5. But it is not that rare. I mean, if you look at the entire period, you can see many below -0.5. It's not a regular phenomenon, it happens. Now, this is interesting because there is an asymmetry between La Nina and El Nino. When El Nino occurs, it occurs here, not longer, normally. Quickly goes down. Well, La Nina can persist for a longer time. And the reason is fairly straightforward. When the ocean warms into El Nino, it starts getting rid of the heat very quickly. Unless some the mechanism charges the ocean. But when you are in La Nina mode, the ocean is cold, it's not getting rid of heat anyway. So it will remain there that state a long period. So it is charging right now. So as I showed you last time, it is in the charging mode, and it is possible the next 1 year it will become an El Nino, but not this year. These are the various El Nino and La Nina events to show that there are years in which they occur continuously, La Nina especially. Now, the interesting point is, for our last 20 years, any number of papers are published claiming that due to global warming, El Nino will increase. Okay, I never believed in it, but I saw lots of papers. Ironically, now what's happening is the opposite. Okay, over the past 50 years, La Ninas have increased, and so nobody understands why. As a matter of this issue has not been understood. How global warming affects El Nino and La Nina. Okay? That means there's some problem with the models. There are many models who have been run for the next 100 years. They are saying as the ocean warms, there will be more El Nino. And but what we are seeing in the last 50 years is more La Nina. So this is an unresolved issue. You may want to study some papers on this. Okay. Now let me come to interesting phenomena occurring on the equatorial Pacific. This is the warm water encroaching into the equator. Okay. The warm patches. Okay. And this is what causing those fluctuations of temperature. Now, this is a very local phenomena, occurs more often during La Nina than El Nino, and it is due to waves, not Rossby Kelvin wave that you read about in your courses. It is called tropical instability waves, very, very local phenomena right here. And this has been studied by many people. So, I'm not giving the, yeah. So, this is also observed SSC, showing this warm anomaly from off the equator coming to equator and causing this oscillation. Okay. So, but this doesn't affect the overall development of La Nina. It's just a fluctuation that causes confusion. Now, this has been studied by this paper by Murthukude and Jokum, and studied a very nice paper showing this phenomena simulated by a model, and the observations here. So this phenomena is understood how meridional advection causes this oscillation of temperature, but it is completely localized to this region and occurs more often during La Nina than El Nino, this phenomenon. And now I want to ask, because Venugopal raised the issue about impact of Rossby wave in mid latitude. Yes, I've seen that in 2019. So I want to give two pictures here. This is from 11th to 20th July 15-day average, when the Rossby wave intruded into India. Okay, and then the next 50 days it moved away. Okay? And this was a period of below normal rainfall, and this was a period of above normal rainfall. So this is well documented. The only problem I have, alluded to it many times, one cannot easily prove the cause and the effect. This is a recurring problem in our field. That things take place in a so complicated way, one can only associate. One cannot say that this Rossby wave intruded into India. It's possible that monsoon weakened and enabled the Rossby wave to come down. And I'm not, if any of you have seen it here, let me know. Can anybody do a very careful lead lab and show which is the one leading, which is the one lagging? I'm not seeing it. But this has been discussed for a long time. It's whole of Rossby wave that
Hello?
Or do we?